All right. Let's go ahead and get started. Yes.
How do you find unique max flows and cuts?
Okay. So the question is how to tell if a graph has a unique maximum flow. And I'll answer the cut in a second. So I mean, the first step is compute a max flow. Let's call it F star. This will tell you at least. Okay, here's an example of a maximum flow. Now, the second step here is really not a separate step, because this is, at least if you're running any variant of forward focus, and you've already done this, but you build the residual graph of that maximum flow. And then the claim is that F star is unique if and only if this residual graph is a DAG. So if the residual graph has a cycle in it, then I can push flow along that cycle and update F star, and that will create a new flow with the same value. And so therefore F star is not unique. So if GF star has a cycle, then I can push flow around it, and that creates a new flow that has exactly the same value. Going the other direction is a little bit more complicated, but it essentially boils down to an application of the flow decomposition theorem. So let's suppose that I have some other maximum flow that I'll call F prime. Then if you remember the way that these maximum flow algorithms work, the general strategy is you find some flow, and then you recursively compute a maximum flow in the remaining residual graph. You add the flow that you start with to the residual flow that you find in the recursive call. So I'm gonna try to do the same thing here. I'm gonna argue that there's a way to get from F star to F prime by pushing flow around in the residual graph of F star. Okay. And the short way of saying that is F prime minus F star is a feasible circulation in this residual graph. So what I mean by F prime minus F star is along every edge, I define the flow value to be F prime of that edge minus F star of that edge. But if it's negative, that means I should send the opposite flow along the residual edge in the opposite direction. And verifying that, so assuming this is in fact a flow, it's going to have value 0 because flow is a linear function of the value is a linear function of the flow. So the net F prime flow out of S minus the net F star flow out of S is going to be zero because F prime and F star are both are both maximum flows. And then you have to verify that this function that you've defined satisfies the conservation constraints at every vertex, and that these values along every edge are between 0 and the residual capacity in the corresponding residual graph. But if this is a feasible circulation in in G star, the flow decomposition theorem implies that F minus F star is a sum of cycles in GF star, which means there are cycles in GF star. GF star is not a DAG. Okay. So then the second half of, well, okay, let me first ask if this is, at least at an intuitive level, if this is clear. If I want to know whether the maximum flow is unique, I push as much flow as I can, and then intuitively I ask, is there another way to push flow around? So I would be adding some flow along something and subtracting some flow along something else, and that would not actually add any value to the flow, it would just cycle around. Yeah? I'm sorry?
Can you explain the flow decomposition?
Oh, sure. So this is one of these standard tools that, like Ford Fulkerson, that you should have like a sketch of the theorem on your cheat sheet. Okay, so the flow decomposition theorem says any flow from S to T in G can, well, let's call this flow F, can be written as the sum of a bunch of paths plus the sum of a bunch of cycles. When I say paths and cycles here, what I really mean is I want to interpret a path as a flow from S to T that has some weight, some constant, it's the same weight on every edge of the path, and 0 on every edge that's not on the path. Okay, so this is really, when I say path, I'm really equating a path with a special kind of flow. And similarly, when I say cycle, I'm really equating the cycle with a special kind of flow that has some fixed value on every directed edge in that cycle, and 0 on every edge that's not in that cycle. Okay, so in the, I think in the notes, the way I said this, it's a sum of path flows and cycle flows. And moreover, every edge in every path and cycle in these flows carries positive flow, meaning F of UV, the original flow that you're starting with, is positive, this F. And moreover, the number of paths plus the number of cycles is going to be at most the number of edges in the graph. And moreover, there is an algorithm that actually computes this decomposition. In time proportional to V times Z. And this VE is the best that you can hope for, because the decomposition itself might consist of omega of E paths and cycles, and each of these paths and cycles might have length up to V. So just writing down a description of the flow decomposition, I have to write down all of the edges in these paths leading from S to T and the weight of the amount of flow that I send along it. Similarly for these cycles, I need to write down all the edges in the cycle and the amount of flow I send around it. The number of numbers that I have to write down in order to describe this decomposition could be as large as V times E. An example. Sure. So let me make up a flow. Let's go this way. Actually, let me direct this edge upwards so we can get some cycles. 5, 3, 8, 2, 6, 8 in, 3 out there. That's 5 out there. 4, 10 out. It's too much. Let's call this 1 and this 1, and I've got 5, 6 in. Okay, so here's a flow. Okay. The way that the proof of the flow decomposition theorem works and the way that the algorithm for constructing the flow decomposition works is the following. If the flow is 0 everywhere, you're done. The 0 flow is equal to the sum of 0 paths and 0 cycles, and so there's nothing to do. Otherwise, I look at the graph of edges that have positive flow in them, and the first thing I ask is, are there any cycles in this graph? And in this particular case, I can see a cycle from the lower left vertex to the upper left, to the upper right. So I can identify a cycle here. And now, among all the edges in that cycle, I say, well, the minimum flow value along that cycle is equal to 3. So I'm going to say, okay, I'm going to write down the cycle over here, and I'll write down the number 3. And then I'll subtract 3 from each of those, the flow along each of those edges. So this becomes 0, 5, and 3. And now that I've dealt with the cycle, this edge has flow 0, so I just get rid of it. And now I have a graph, a flow that has one fewer edge in it. And so by induction, the rest of the algorithm will recursively compute the decomposition. Yes? Yes. So how do you find a cycle in a directed graph? Well, there's actually a two-word answer. Bellman-Ford will find a negative weight cycle, right? So what is the first thing that you do to a graph that doesn't have any cycles in it? Topological sort. So what you do is you try to topological sort the graph, and it doesn't work because you find a cycle. And that you want to do topological sort anyway because the next stage of the algorithm, if I'm in this state where there is no cycle in the graph anymore, it's a DAG. Now one of the things that's going to fall out of doing this topological sort is I'll be able to find a path from S to T. Again, I guess it's whatever for search. So at this point, I would write down the path. And I look along all the edges of the path, and I notice the minimum flow value in this case is, again, 3. So I write a 3 here. And so I'm going to reduce all of these values by 3, which means this edge is just going to go away entirely. 2, 3. And now, again, I've reduced the number of edges in the graph by 1, and so I've got a simpler graph, which by the inductive hypothesis, I'll get the decomposition for. Yes?
Yeah, this makes a lot of sense intuitively, but how can you guarantee that there won't be a dangling edge at the end of the graph that you can never get to?
Okay, that's an excellent question. How do I know that this is always going to work? And there's an invariant that this algorithm maintains, which is at all times, the graph that I have left describes a flow from S to T. Right? Which means if I wander along any edge in this graph into a node, that means there's flow into that node, and then by the conservation constraint, there must be flow out, and so I can always take the next step outward. The only place I can ever get stuck is at the only node that has more incoming flow than outgoing flow, which is T. Okay. So, I can run this for, I guess it would end up being 3 more iterations where I'd say, okay, here's 1 unit along this path, and then 1 unit along this path along the top, and then 1 unit along this path along the bottom. And then all together, I would decompose that original flow that I started with into 1 cycle and 4 paths. Okay.
So that 1 cycle is called a circulation? Is that what circulation?
Just by, so a flow that has value 0, you'll always be able to find cycles. So a sum of cycles or a flow with value 0 is called a circulation. So in particular, a single cycle by itself is a circulation, as an example of a circulation. Okay. Yeah.
Is this always unique?
No, it's not. So this was not the only path that I could have chosen. I didn't have to do this long zigzag. I could have gone along the top. And if I had gone along the top, actually I would have eaten up one of the top edges, and then I wouldn't be able to find the zigzag cycle. So you're not always going to get a unique decomposition, but you will get a decomposition. So in particular, when you're doing assignment problems, you reduce an assignment problem to a flow where you have, okay, this is a bipartite graph, and I have a source S on one side and a target T on the other, and all the edges oriented from left to right. Because the graph itself is a DAG, the flow inside that graph will also be a DAG, and you'll never get any cycles. You'll just get paths. And the paths will go from left to right, from S to the first set to the second set to T. And that flow decomposition in the paths decomposes the flow into the assignment that you want. Right? Every path goes from the source to a paper, to a program committee member, to the target, or from the source to a class, to a building, to a time, to hold the exam, and then to the target, or from the source to a day, to a music genre, to a DJ, to the target. Each of those paths is one of the assignments that you're trying to compute. Yeah.
Can you do the universal hashing problem on last year's midterm?
Okay. Yes, but let me make sure that there are no more questions about this particular problem first. Yeah.
So do we need to get rid of all the cycles before the pass? Because otherwise we might.
No, this is not. So the other way that you could prove this is to say, does the flow have positive value? If so, then I can find a path. Otherwise, the flow must have value 0, and then you look for cycles.
So what's the difference between this and the greedy flow?
So with the greedy flow question, you're starting with a graph where you just know the capacities and you're trying to compute a flow. Here, you're starting with the flow. You're guaranteed that the weights on the edges obey the conservation constraint in the input.
So when does a greedy flow work?
When the maximum flow saturates every edge, or when you get very lucky. So the question was, when does the greedy flow algorithm work? Basically never.
Yeah, but in the exercise it says the greedy flow is very capacity. It's because you precisely the path to any.
I'm actually no longer convinced. The solution that I actually had in mind for that it's not clear that it works. So there's a question here about the greedy flow fairy. So the question is, suppose I augment my implementation of Ford Fulkerson with a magical fairy that will tell me, augment along this path, then augment along that path, and with exactly the right choice of paths, after order E iterations, I should be done, because whatever max flow I compute, I can decompose with this into a bunch of paths. The subtlety is when you run Ford-Fulkerson, when you push flow along the path, the amount of flow you push is based on how much capacity you have left. And that's not necessarily the same as the amount of flow that you would get along that path in the decomposition. So, yeah, I have actually edited that particular part of the question out of the notes at this point. Yes?
Did you say how this relates to the original question on finding
Okay. So the question was, how do you find whether a graph has a unique maximum flow? And part of the proof was, suppose the maximum flow in the graph is not unique. There's two maximum flows, F star and F prime. Then some definition chasing implies that this function, F prime minus F star, is a feasible circulation inside this graph.
Yeah.
So the flow decomposition theorem tells me that I can take any circulation and decompose it into a set of cycles. Therefore, there must be a cycle.
Okay. Thanks.
Okay. The other half of your question was, how do you tell when a graph has a unique minimum cut? This one I'm not going to want to go into quite as much detail, but here's the basic idea. So again, I'm going to compute a max flow, F star, and I'm going to compute the residual graph in this. And I know that, here's G of F star. I know that once I've computed a maximum flow, I can extract a minimum cut from it by saying, what vertices can I reach from S versus everything else? So again, I'm applying whatever first search in this residual graph, starting at S and saying, oh, well, what can I reach? This subset of vertices, I could call this subset of vertices S, and everything else I could call T, and this gives me a minimum cut. But there's another way that I could compute a minimum cut, which is to start at T and walk my way backwards to look at all vertices that can reach T, essentially running the reachability algorithm backwards. And so this gives me a different minimum cut. So over here, S is everything that I can reach in S, and T is V minus S. And in the other direction, I have T is everything that can reach T. Not as reachable from T, but that can reach to T. The minimum cut is unique if and only if these two cuts are the same. If S and S prime are equal and T prime are equal, then there's one minimum cut. If S and S prime are different and T prime are different, then clearly I found two minimum cuts. So the harder thing to prove is that if these two cuts are equal, then these are the only cuts. And this proof is essentially brute force. It's essentially sort of definition chasing about what a cut is.
We have unique cuts. Do you have any unique characteristics in the flows?
I'm sorry?
Do you have a unique minimum cut? Do you have any uniques in the flow?
No, not necessarily, because so I might very well have a unique minimum cut, but nevertheless, in the residual graph, I might have a cycle sitting over here. that I can push flow around. So the cut might be unique even though the flow isn't. And similarly, the cuts might be different even though the flow, the residual graph is a DAG. So the uniqueness of these two things is just completely different. Yes?
If I'm given a flow, maximum flow, can I say that I have at most 2 minimum cuts?
No. Actually, there might be several intermediate cuts between these two.
Is there a way of finding them?
That is an interesting question. Probably there's a way of finding them in some small time each, but there might actually be an exponential number of minimum cuts. So as a stupid example, I could imagine a graph that looks like this. I just mirror this all the way from S over to T. So I have a bunch of these crossovers, and every edge in here has capacity 1, except the edges on the ends have capacity 2. And the maximum flow has value 4. I saturate every edge. Now, how many different ways are there to separate, basically almost any subset of the vertices defines a minimum cut at this point.
So in this case, how can I find an upper binding edge? Because the way I think about it is this edge needs to be on all the cuts. So that if I increase the capacity by 1, I also increase the overall max flow.
In this particular case, there are no upper binding edges. Right. So the question is, right, for example, this is a minimum cut, but so is this, and those two cuts have no edge in common.
So in general, how would I do that?
In general, how would you find an edge that lies in every minimum cut? I believe, and then this is something to do a sanity check on. I believe what you can do is compute these two minimum cuts and see what edges they have in common. I believe if these two minimum cuts share edges, those edges are actually going to be part of every minimum cut. These are in some sense the leftmost minimum cut and the rightmost minimum cut. And everything else is between those two in some formal sense. So if they meet somewhere, then everything in between is also going to go through that. Yes?
So that means when you have your max flow at star, you have this residual graph, but if you have another one,
I'm sorry, I'm having trouble hearing you.
so that now you have a max flow at star and you have this residual graph.
Yes.
But when you have another max flow, what are you
Oh, okay. So the question is, why wouldn't I get a different result if I started with a different maximum flow? And the answer is, in order to get a different result, I have to take the difference between these two maximum flows, that circulation that I find, somehow has to include a cycle with an edge that crosses that cut. I have to push flow, some edge that's saturated I have to remove flow from. So I need a cycle that contains one of those saturated edges. The problem is that all of the edges that cross from S out of S have 0 residual capacity. There is no way to send flow out of S in the residual graph. And therefore, there are no cycles that look like this. And therefore, even if I add more cycles to create different maximum flows, all of the edges crossing that cut will always be saturated, and all the edges going backwards will always be empty. Yeah?
What's the case where a minimum cut would be greater than the maximum flow?
That can't happen by the max flow min cut theorem. The max flow min cut theorem says the value of the maximum flow and the value of the minimum cut are equal. Yes.
So going back to max flow, is the intuition why if there's a cycle, it's not unique max flow is because you can go around the cycle multiple times?
No, you just have to, if there's a cycle in the residual graph that say every edge in that cycle has capacity greater than 1, I can push 1/1,000,000th unit of flow around that cycle and get a different flow. Or 1/square root of pi, or in fact, if the case is either there is one maximum flow or there are an infinite number of maximum flows. Yeah.
So back
Sorry.
down to the min cut.
Yeah.
Here, I guess like when we're using this method to show if these two are equal, it's a min cut. That that's a unique min cut. How can we make sure that we don't miss like any intermediate cuts? Like you mentioned that there could be like multiple min cuts, right? Not just these.
I mean, essentially what you have to argue is that on the S side of every minimum cut, say I have S double prime, T double prime, is some other minimum cut. Then S is a subset of S double prime, and T prime is a subset of T double prime. This is grindy, boring, so not a good exam question. If it's relevant, feel free to use this. It won't be relevant. But it's good to think about these things just to get used to the underlying structure. There was a question about universal hashing that I want to get to next. But are there any other last questions about the decomposition?
If you're going to determine the edge, whether it's belongs to the
Well, okay, so I have to poke at the language a little bit. You said, how do I find an edge that belongs to the minimum cut?
and
You want to find,
one specific edge.
well, I mean, I find all the nodes in the residual graph that are reachable from S, call everything else T, and then find any edge that goes from S to T.
Can we do the argument? Can we find another augmenting pass?
No,
If there's a circle, no.
no, I mean, if it's a maximum flow, then there are no more augmenting paths in the residual graph.
Just from the specific.
I'm not sure I understand the question. Okay, all right. Okay, so there was a question about universal hashing. Can you tell me the question, please?
You have suppose we hash a set of n items to a table size n equals to 1 using the hash function h chosen uniformly for n system universal family assume square root of n is a integer.
Assume the square root of n is an integer. Oh, thank you. Okay. So, so the definition of universal is a set of hash functions is universal if, when I choose a hash function uniformly at random from this set, the probability of two different items colliding is at most 1 over m. And this is for all items in the universe X and all items in the universe Y that are different. Okay, the only randomness has to do with the hash function. So the problem says, suppose I have a set of n items that I want to hash into a table of size m, which is equal to 2n, and assume, because I'm going to be using square roots in the problem, that square root of n is an integer. So part A is prove that the expected number of collisions is at most n over 4. Okay, so the first thing to do is to say, what exactly are we counting? And so I look at the problem statement and it says, for any fixed hash function h, a collision is an unordered pair of distinct items x not equal to y, such that h of x equals h of y. A collision is a pair of items such that they have the same hash function. Okay, so what I'm going to write then is I'm going to do the usual decomposition of a random variable that counts something into a sum of 0, 1 variables, one for each thing that I might count. So in this particular case, what I'm summing over is all unordered pairs of items, all pairs of things that might collide. And so I can express the total number of collisions as a sum over all pairs xy of 1 if h of x and h of y are equal and 0 otherwise. And as usual, I can then decompose this expected value into a sum of probabilities. Okay. Now I know what the probability is because by the definition of universal, this probability is at most 1 over m. And now the only question is, how many things am I summing over? So out of the n items that I'm putting into the hash table, how many ways are there to choose 2 of them named x and y? Given n things, how many ways are there to choose 2 of them? Right? So this is equal to n choose 2 over m. But I know what n choose 2 is. And I know what m is. And so this is n minus 1 over 4, which is indeed at most that's strictly less than n over 4. Okay, good. Part B. Prove that the probability that the number of collisions is at least n over 2 is at most 1/2. Any ideas? Markov's inequality. Okay, so this, because the number of collisions is smaller than or equal to n over 4, this probability here is less than or equal to the probability that the number of collisions is at least twice the expected number of collisions, which by Markov's inequality is at most, actually, let me do this a bit more directly from Markov. I can write this as, this is the expected number of collisions divided by n over 2. This is just Markov, which is by the previous argument at most n over 4 over n over 2, which is 1/2. Okay. Markov's inequality says the probability that a non-negative random variable x takes on a value at least z is the expected value of x divided by z. And I've just plugged in the appropriate things. Okay. Part C. Prove that the probability that some subset of more than square root n items all hash to the same value is at most 1/2. Okay. So, and there's a hint. Use part B. So, the obvious thing to try to do, or one natural thing to try to do, is show that this probability down here is smaller than that probability that I bounded to part B. Okay. And so let me think a little bit. If I have a subset of more than square root of n items, how many collisions do I have? And this goes back to the question, what is a collision? A collision is a pair of items that have the same hash value. Okay, so out of this subset of, let's say, k greater than, if I have a subset of k items that all have exactly the same hash value, how many pairs of those items have the same hash value? K choose 2. Okay, so this is at most the probability that the number of collisions is at least, well, I want to say k choose 2 here, where k is bigger than square root of n. The smallest value of k that makes sense here is square root of n plus 1. Bigger than square root of n means at least square root of n plus 1. So let me go down off to the side here. Square root of n plus 1 choose 2 is square root of n plus 1 times square root of n over 2, which is slightly larger than n over 2. Right? So this is at most the probability that the number of collisions is bigger than n over 2, which is at most 1/2 by part B. Now, I want to point out about something about these inequalities. This, having a subset of more than square root of n things all hashing to the same bucket, that is not the only way to get this many collisions. That's why there's a less than or equal to sign. And then because this number n over 2 is actually slightly smaller than square root of n plus 1 choose 2, if I say the probability the number of collisions is at least this, let's call this number x, and that has to be less than or equal to the probability that number of collisions is bigger than this number that's slightly less than. Right, as I say, what's the probability that I'm above this bar? Well, that's less than the probability that I'm above this lower bar. Okay. Now, the last question in this, there was a bug in the original version that I asked on the exam, which meant everybody got lots of extra credit. Assume H is strongly for universal, which is the same as for uniform, meaning that given any 4 distinct items and any 4 not necessarily distinct hash addresses, the probability that W hashes to I and X hashes to J and Y hashes to K and Z hashes to L, all that together is at most 1 over m to the 4th, what you would expect from an ideal random hash function on those 4 values. Then what you want is to prove that this probability of there's some subset of size square root of n into that hashes into 1 hash value is big O of 1 over n. Okay. So the solution that I had in mind, which is the reason why I need to assume that H is 4 uniform, is that I want these events, h of x equals h of y, to be pairwise independent, which means that I can now use Chebyshev's inequality instead of only using Markov's inequality. So using Markov's inequality, I don't need to assume anything about the variable number of collisions except it's non-negative. I don't need to assume it's a sum of indicator variables. I don't need to assume that it's an integer random variable. I don't need to assume anything except it's never negative. And then Markov's inequality still holds. For the version of Chebyshev's inequality that we've seen in this class, in order to apply it, I need to know that the variable that I'm trying to bound is the sum of indicator variables that are pairwise independent. Now, if I look at a pair of collisions, that's a pair of pairs of items. That means a pair of collisions involves 4 different items. And so I need to know that knowing what these two hash values are and knowing what this third hash value is doesn't give me any information about what the fourth hash value is. That's what 4 uniform means. So only then can I conclude that these 2 pairs of pairwise collisions are actually independent from each other. And then if I do that, Chebyshev's inequality says the probability that the number of collisions is bigger than n over 2. We'll remember what Chebyshev's inequality actually says. The probability that x is at least 1 plus delta times the expected value of x is at most 1 over delta squared times the expected value of x. So in this particular case, 1 plus delta, remember the expected value of this is about n over 4. So the 1 plus delta that I want to plug in here is 2. So the delta that I want to choose to apply Chebyshev's inequality in this case is 1. Okay. So then what I'm going to get here is this is going to be at most 1 over the expected value of x. And I go back, the expected value of x is n minus 1 over 4. And this is indeed big O of 1 over n. There is another way to derive this, which is to ask, what is the probability that square root of n things hash to value 1? What is the probability that square root of n things hash to value 2? All the way up to the value m. And then it turns out if you apply the fourth moment method, the probability of getting square root of any things in any particular slot is going to be 1 over n squared. And then you use the union bound to sum over all those slots. And again, you get 1 over n. We haven't played with the fourth moment stuff, so this is not the way that I would expect anyone to be able to do it. Okay. This is beyond what I would expect to be a fair exam question. Parts A through C, perfectly fair. 1 line each, 2 lines each maybe, a little bit of math. But this leap from 4 uniform, meaning that these collisions are pairwise independent, I think is just a little bit over the edge from what I can actually ask you to do. Yes, in the back. I'm sorry, I'm having trouble hearing you.
We need to remember the different format of the hash functions, like the tablet the other, like multiplication hash.
Any specific details like what is multiplicative hashing or what is linear probing or what is cuckoo hashing? if it's relevant to the problem, I will define them in the problem. That's not what I said. Okay. I said I will define them, but the reason to put it on your cheat sheet is not so that you can look them up. The reason to put them on your cheat sheet is so that when I define them, you go, oh yeah, I remember this. And you're not learning it for the first time. It's on there as a reminder, but if you write it on your cheat sheet, it's going to be easier to recall what's going on, easier to remember what you understand. So, you know, a lot of these things we're not necessarily going to be asking you about the specific fine details of some, you know, technical variant of these things. But as a general rule, yeah, you should know what linear probing is. You should know what the general idea of multiplicative hashing is. But as I said, for the specifics that we need you to know, we will tell you.
We're going to be given like Chebyshev equality.
Yeah, there's the last page of the exam is the last page of midterm 1 plus a few more things. Yeah.
Can you describe in one sentence linear probing?
Sure. Okay, linear probing. You compute a hash value and you look in that spot in the table. And if it's full, you go to the next one. And if it's full, you go to the next one. And if it's full, you go to the next one until you find something that's empty. If you reach the end, you start over at the beginning. Okay, you use the hash value to start a linear scan. Okay. Multiplicative hashing. The idea is that I pick some so-called salt parameters at random, and then I have this function that depends on these parameters, which is at its core ax plus b, but then to sort of fold up the range of values into a small range, the first thing I need to do is mod by some prime number. Okay, and each of these random values a and b, I may as well choose from the range of integers between 1 and p. Right, so p is prime. And then the second step is that gives me some number between 0 and p minus 1, but I need to map that down to a number between 0 and m minus 1. Okay. So I take this mod m. And generally speaking, this prime is relatively large compared to m. Say, if you're hashing 32-bit things, you would pick a prime that needs all 32 bits. But as long as p is sufficiently larger than m, this family of hash functions is nearly universal. Actually, with the plus b in there, it is actually universal. Yeah. Without the plus b, it's nearly universal, which is good enough for most purposes. Yes? Yes.
So when you say you have at least 2 n plus 1 to collision,
Uh-huh.
are you making sure that it's like n items of them have to be exactly the same hash value?
So what I'm saying here is some subset of at least n minus 1 things all have exactly the same hash value. Every pair of items in that subset is a collision. So I have square root of n plus 1 things, and every pair of them gives me a collision. So I have at least square root of n plus 1, choose 2 collisions.
But these pairwise collisions, do they all have the same hash value?
Well, by definition, they have the same hash value because I've started with a set of items that all have the same hash value.
root and items have the same hash value?
Right, so what I'm saying is, suppose there is a set of root n things that have the same hash value.
How many?
Then there are at least this many collisions. Because if A then B, that means the probability of A is less than or equal to the probability of B.
You're gonna go the other way.
No, I can't go the other way. This is not an infinite length.
Are we going to be given like the definition of universality, uniform?
Again, I will give you those definitions in the problem statement.
Is universal a stronger constraint than a uniform?
No, it's not. So the question is, what's the relationship between universal and uniform? So universal means the probability that any particular pair collides is at most 1 over m. 2 uniform is a stronger statement that implies universal. This says the probability that x hashes to I and y hashes to j is equal to 1 over m squared. Okay, this is for all items x not equal to y and all indices I and j, whereas this is for all x not equal to y. So the second condition implies the first, right? So the way there are m different ways of getting a collision. I can get a collision at address 1, a collision at address 2, a collision at address 3. If the hash function is chosen from a 2 uniform family, each of those choices has probability 1 over m squared. And so summing up those m choices, I get an overall probability 1 over m per collision. But it's a one-way implication. The opposite implication is not true. So there are universal families of hash functions that are not 2 uniform.
Yeah, if you assume that H is 4 uniform, does that gonna change the expectation number of operations that you have?
So 4 uniform implies 2 uniform implies universal, right? So, but if I say, what's the expected number of collisions, then by linearity of expectation, independent of what the hash function family looks like, this is going to be the this is going to be the sum over all pairs xy of the probability that h of x is equal to h of y. Just linearity of expectation. Remember, linearity doesn't require any assumptions about independence. It doesn't require, it could be, linearity of expectation applies even if the hash function maps everything to 1. Right? It doesn't matter. And now I look at what does 4 uniform imply about this probability. Well, it implies universality, which means this probability is equal to 1 over m. I think one weak thing you could say is if it's 4 uniform, you notice that that's an equal sign over there, equals 1 over m squared for 2 uniform, whereas universality it's a less than or equal to. So that would mean that instead of saying this is at most n choose 2 over m, if it's 2 uniform or 4 uniform or 72 uniform, you would say the expected value is equal to n choose 2 over m. But we're generally interested in upper bounds on these things more than lower bounds. Yeah.
Number 3, how did you make the jump from saying greater than square root of n items have the same value? Sorry, for part B, not part C.
For part D,
Yeah, how did you go from square root of n to 1 hash value equals number of collisions greater than the number?
exactly the same as part C. Well, I mean, we went through this part of the argument already, that some subset of more than square root of n items is less than or equal to some number of collisions is at least n over 2. So I just pulled that inequality out and plugged it in for part D. The only difference is that I'm using Chebyshev's inequality to bound this probability instead of Markov's inequality.
Like, if you'd done this with square root of n plus 2, would it be a less strong claim?
No, it would be a stronger claim, but then I would not be counting the possibility that the exactly square root of n plus 1 thing.
Okay.
I mean, the reason that it says strictly more than square root of n instead of at least square root of n is that square root of n choose 2 is slightly smaller than n over 2.
Yeah.
And I just needed to aim for n over 2.
Okay.
Yeah.
So, you had a family of multiple binary hash functions.
Yes.
So they're near universal because of the question asks us to prove that they're not pairs.
Not a good exam question. It's an interesting homework exercise, maybe, but not a good exam question. Yeah.
Moving away from hashing.
Okay.
For streaming, there's only one question at the end of the and you gave it to us for homework. So what can we like expect for streaming? It's just the example you gave us there.
This is an unfortunate fact that there's really very little in the way of sort of sensible streaming exercises that we've been able to come up with that are battle tested, and the exams are not the right place to battle test these questions. But the kinds of questions that we might ask are similar to like the analysis of streaming algorithms, where you say, okay, I mean, streaming is kind of really just an application of hashing. And so, some of the tricks that come into play with streaming algorithms are, suppose I keep multiple copies, and what's the probability that some of it happens in every copy? Or I take several estimates and use the median as a guess. This is not really something that is specific to streaming. It's just, it's useful in that context. But it's also useful in other contexts that are just related to hashing. Yeah.
So for the metric of
Uh-huh.
question 4, can you solve part where we're not really sure the rules of that?
Okay. So this is the last question in the hashing notes. Oh, by the way, whose midterm is this? Who's this? The question is, suppose I have an open address hash table of size m. I'm using to store n items where n is at most m over 2. Assume I have an ideal random hash function. So when I talked about hashing, I said at the very beginning that a sort of first order straw man that people use to study the behavior of hash functions is, let's assume h is totally random, and that's totally unrealistic. But nevertheless, a lot of applications of hashing still make that assumption. For example, when we talk about Bloom filters, we use ideal random hashing. When I talked about locality sensitive hashing, we assume something about ideal randomness. And there are some applications where we actually don't know how to weaken the assumption. Ideal random means k uniform for all k. So whatever independence you want, it's there. Whatever uniformity you want, it's there. Okay. So let xi be the number of items x such that h of x is equal to I, or if you want to be more concise, you could say something like this. This is the number of items that you would sorry, I'm not reading the question, I'm improvising, excuse me. Number of probes for the ith insertion. This is an open addressed hash table. In the context of an open addressing hash table, what ideal random means is not only that the initial probe into the table is at a uniformly random, totally independent location, but that the entire sequence of probes is also a uniformly generated permutation of the array. So the hash function, in some sense, is a permutation of the indices, and I probe the hash table at each of those indices in that permutation. Okay. And then I'll call this max x sub I, we'll call that x. Okay. So part A says prove that the probability that x sub I is greater than k is at most 1 over 2 to the k for all I and k. Okay. The probability of getting a long probe sequence given this ideal randomness assumption should decay exponentially with the length. And the key is this inequality here that says the number of items, the maximum number of items that I consider storing in the table is at most half of the table. And that means that the probability of picking a random spot in the table and probing it and that it's empty is at least 1/2. Okay, so this is the probability that I probe k random addresses, and they're all full. But the probability of any particular address being full is less than 1/2. Okay. So this is going to be, because I have uniformity here, ideal randomness, this is the probability that any particular address is full to the k, but the probability any particular address is full is at most 1/2. So no tail inequalities here. I'm just arguing from first principles. Part B says prove that the probability that x sub I is at least 2 times log base 2 of n is at most 1 over n squared for all I. The proof of this is set k equal to 2 log n. I mean, 2 to the 2 log n is n to the 2 log 2, which is n squared. Part C, prove that the probability that x is at least 2 log n is at most 1 over n. Now there's no I anymore. Right, so here the answer is, again, 2 words, union bound. What this means is the probability that the maximum value is bigger than 2 log n is the same as the probability that x1 is at least 2 log n plus the x2 and x2 is 2 log n and sorry, I'm going the wrong way. Am I going the wrong way? Or. Yes, or. The probability that x1 is big, or x2 is big, or x3 is big, all the way up to the probability that the xn is big. Each of those probabilities is at most 1 over n squared, and so the probability of one of those events being holding is at most the sum of the probabilities of those individual events, the union bound sets. Right, so let me write this out in a bit more detail. So the probability that x is bigger than 2 log n is equal to the probability that x1 is bigger than 2 log n, or x2 is bigger than 2 log n, or xn is bigger than 2 log n. And then the union bound says this is at most the probability that x1 is bigger than 2 log n plus the probability that x2 is bigger than 2 log n up to n. And each of these is at most 1 over n squared. Okay. Last question, D. Prove that the expected value of x is big O of log n. And this is the part where you were specifically asking. Okay. Okay, so the expected value of x, by definition, is the sum over all values of little x, x equals little x. You can also write this as the sum over all little x of the probability that x is bigger than or equal to little x. Okay. So we know something about the probability of x being big. So the probability that x is big is tiny, right? So what I'm going to do is I'm going to take this version and I'm going to write it in I'm going to split this sum into 2 different parts. X equals 1 to 2 log n plus everything else. X equals 2 log n plus 1 up to the maximum value that it could possibly be, which is n. If there are n things in the table, then after probing n different things, the next one will find something. X times the probability that x equals little x. Okay. Now I'm going to do some inequalities here. The first thing I'm going to do is argue that I can replace that first little x with 2 log n and still get an upper bound. Okay, so this is sum over x equals 1 to 2 log n of 2 log n times the probability that x equals x. And then the other thing I'm going to do is replace that. So sum from x equals 2 log n plus 1 up to n of n times the probability that x equals x. Okay? The second thing I'm going to do is realize that the sum doesn't actually depend on, this factor 2 log n doesn't depend on the index of the summation, so I can pull it out, right? Likewise, I can pull this n out. It's a shame that you can't actually do this on your exam. Okay. And then I'm going to look at these summations and see what they actually represent. The summation over here on the left is the probability that capital X is at most 2 log n. Well, I actually know an upper bound for that. Does anyone want to tell me what it is? 2 log n times what? 1. It's a probability. Therefore, it's at most 1. Plus n times, well, I actually know something about this probability over here. It's at most 1 over n by part C. This is 2 log n plus 1, which is big O of log n. Okay, so I basically say there are 2 possibilities. X is big or X is small. If X is small, the probability part doesn't matter. I might as well assume it's 1 because that's only going to add something small to the expectation. If x is big, well, I don't care if x is big because the probability of x is big is small, and so I'm only going to add something small to the expected value. And so I only end up adding these small things. Yeah?
You didn't use it, but can you explain the intuition behind the third equals part below, like where you wrote the steps?
Oh, the question is about this? Okay. Does anybody have questions about the specific problem before I go to that equation that I didn't use?
Sorry, what was it one again on the episode of last one?
It's a probability. All probabilities are between 0 and 1. This summation is the probability that capital X is at most 2 log n. Or, to emphasize the important part, it's the probability that and therefore it's at most 1. Okay, so there's this question about this expression for the expected value. When we talked about Markov's inequality, I tried to show a picture that at least gives you some intuition about why this is true. And unfortunately, this is going to be the last thing because we're running out of time. The idea is I'm going to plot this function, probability that x is greater than big X is bigger than little x, as a function of little x. This is a step function, but it's monotone, non-increasing. Okay. At various integer values of x, this thing is going to go down. But now, if I look at a particular stripe here, okay, on the one hand, the width of this stripe is x. On the other hand, the height of this stripe is the probability that capital X is equal to x, because this value is the probability that it's greater than or equal to x, and this probability is the probability that it's greater than or equal to x plus 1. And I'm subtracting those two values. Okay. So if I decompose the area under this curve by breaking it up into these horizontal rectangles, what I'm going to get is that the area is equal to the expected value of x. But on the other hand, if I split it into vertical rectangles, what I'm going to get is the height of every rectangle, the width is going to be 1, and the height is going to be this value. Right, so on the other hand, this is the sum of the probability that okay. I will post this video now so that you can refer to it for the next 2 hours, along with the notes. All right. See you in a couple hours. Thanks. I posted on the webpage. It's in 22. It's in the second floor conference room.
And I have a question about the 4 uniform. Can you explain again why it has to be 4 uniform?
Oh, for this particular, where was it?
Hashing thing.
I need to be 4 uniform because I need to know something about the independence of pairs of events where each event involves a pair of hash values. So there are 4 hash values.
Why can't you just assume for like 1 pair?
1 pair of what?
Hash values.
Because that only tells you about 1 collision. And I need to know that pairs of collisions are independent.
Oh, okay.
So a pair of collisions being independent means I know something about the independence of 4 different hash values.
Okay, that makes sense.
So we have new on spanning trees.